In this video, I'm going to run through the information you need to know for the GCSE AQA Topic 1 Energy. So the first part of this unit is to look at the forms of energy. A way to remember all the different forms, you need to know 12 of them for the exam, is to remember this rhyme. So most kids hate learning GCSE energy names in science. By remembering that rhyme, we can take the first letter of each of the words and we can then use them to remember the forms of energy. So the first one we look at is magnetism, which is the energy associated with magnets or magnetic materials. The K stands for kinetic, which is the energy something has if it's moving, sometimes known as movement energy. H stands for heat, which is any energy that's to do with heating things up. We tend to use the better key term here, thermal energy, rather than heat energy in science. The L from learning stands for light, and that's light energy, so anything that emits light is emitting that form of energy. When we get to GCSE, we have to take each of the letters in turn. So G stands for gravitational potential energy. That's the energy something has if it's held above the ground. So the potential energy that if it was released, it would then begin to fall. The C stands for chemical energy. That's the energy such as the one stored in batteries or cells. It's also the energy stored in chemicals such as fossil fuels that are released during chemical reactions. S stands for sound energy. So that's the energy that basically is produced by vibrations in the air that then go on to lead to sound waves being detected by your ears. You've then got E in GCSE standing for electrical energy, so it's the energy of moving charge around a circuit. You also have another E in energy for elastic potential energy. That's the energy stored when you stretch an elastic band. You've got N, which stands for nuclear energy, and that's the energy released in nuclear reactions and stored in the nucleus of the atom. The I stands for internal energy, and the internal energy is the energy of a thermodynamic system, and it's the sum of the kinetic energies and the potential energies of the particles that make up the thermodynamic system. Finally, we have strain energy, which is the energy released when a molecule rearranges itself in a chemical reaction, and that's the energy released from there. It's worth pointing out that the forms of energy are different to energy sources. So, for example, solar energy is light energy that comes from the sun, whereas wind energy is the kinetic energy of moving air. So wind energy and solar energy are two energy sources which can be used to produce electricity, whereas the energies we've looked at here, the forms of energy, that's just the transfers and stores that we need to look at. As we move on to look at energy transfer in a system, energy can be transferred usefully, stored or dissipated, but cannot be created or destroyed. That concept is often known as the conservation of energy. You also need to be aware that when energy transfers take place in a closed system, there is no net change to total energy. So the amount of energy before is equal to the amount of energy afterwards. You should also be aware that in all system changes, energy is dissipated to the surroundings, which basically means it spreads out to the surroundings, so that it's stored in less useful ways. Unwanted energy transfers can be reduced by using thermal insulation or through lubrication of moving parts. So if you want to reduce the amount of energy transferred in a thermal system, you need to insulate that system by using an insulator. Or if you want to reduce the energy transfer in a system which is moving, you need to lubricate the parts that move. As we look at thermal conductivity, you need to be aware that the higher the thermal conductivity, the higher the rate of energy transfers. And that makes sense because a more conductive material will transfer energy through to a quicker rate. You should also be aware then that the rate of cooling for a building depends on the thickness of the walls and also the thermal conductivity of the walls as well. So you can reduce the rate of cooling by increasing the thickness or reducing the thermal conductivity. We're now moving on to look at energy systems. A system is an object or group of objects, and there are changes in the way energy is stored when a system changes. And we're going to look at one example of this. So the example we're going to look at is the ball, which is highlighted here, and it's being thrown into the air. As soon as the person throws the ball into the air, we can see that the ball is going to have kinetic energy, and the store of kinetic energy will be relatively high. But that store will decrease as the ball travels upwards in the air. So as the ball travels upwards, the kinetic energy store decreases as the gravitational potential energy store increases. Because the ball's going higher up in the air, so its gravitational potential energy is getting greater, but we remember you can't just create or destroy energy, so the energy being transferred from the store of kinetic into gravitational. You also need to be aware that some of the energy will be lost from that transfer, so not all of the kinetic energy will convert into gravitational potential energy. Some of it will go into increasing the internal energy store of the surroundings. We could also take into account the person throwing the ball now and look at their system. So the person who's throwing the ball, well, they have a store of chemical energy inside their bodies. That chemical energy will decrease, and the decrease in chemical energy will be equal to the increase in the kinetic energy as the ball is thrown upwards. When you come to answer exam questions, they really like you to talk about the increases and decreases in the different stores of energies. So here we can see that for the person, the chemical energy store goes down, the kinetic energy store originally increases, but then that will decrease as the ball gains in height, and the gravitational potential energy store will increase. And the key thing that is increasing throughout this is the internal energy store of the surroundings. So the particles in the air will become more energetic as the ball moves around the way. We're now going to look at work done, and work done is just another name for energy transfer. When you want to move any object, you need to do work to it in order to make it move. And we can work out the amount of work done in moving an object using the formula that's shown below. So work done is equal to the force multiplied by the distance moved in the direction of that force. Work done, remember, is measured in joules, force is measured in newtons, and distance is measured in meters. I've included the formula triangle there in case you want to use it. When work is done to a system, the system gains energy, so energy is transferred into that system. But when work is done by a system, the system will lose energy, and energy is transferred away from the system. So by doing work to a system, you can increase the energy store of that system, but when a system does work, the energy store of the system decreases. The work done equation is one of those equations that you will need to learn. We're now going to move on to two more equations that you need to know, which are kinetic energy and gravitational potential energy. Kinetic energy of an object is the energy an object has by virtue of its motion. The amount of kinetic energy an object has can be found using the equation kinetic energy is 0.5 times mass times velocity squared, where kinetic energy is measured in joules, mass is measured in kilograms, and velocity is measured in meters per second. You need to learn this equation, and remember that the symbol equation is given as kinetic energy, EK, equals a half mv squared. You could also be asked to calculate the gravitational potential energy. Remember that gravitational potential energy is the energy an object has by being raised a certain height above the ground. The amount of gravitational potential energy can be calculated using the equation gravitational potential energy is mass times gravitational field strength multiplied by height. You should remember that the gravitational potential energy is measured in joules, mass is measured in kilograms, gravitational field strength is measured in newtons per kilogram, and height is measured in meters. On Earth, we take the gravitational field strength to be 9.8 newtons per kilogram. This means an object falling on Earth will accelerate at 9.8 meters per second every second. The gravitational potential energy equation is another equation that you have to learn, and in symbol form, that's written as E equals mgh. You also need to be aware about how to convert between kinetic energies and gravitational potential energies. And you should realise that when you drop a ball from a certain height, the gain in kinetic energy is equal to the loss in gravitational potential energy. This also works in the opposite direction, so if you throw the ball from the ground, the loss in kinetic energy would be equal to the gain in gravitational potential energy. In these types of questions, you usually assume, unless it tells you otherwise, that all of the energy is converted from gravitational potential into kinetic, or all of the energy is converted from kinetic into gravitational potential energy. You should also remember that you have to remember these two equations. They're not given to you on the formula sheet. The exam will expect that you remember them, and therefore they should become part of your revision to make sure you learn them ready to be used in the exam. So we now move on to elastic potential energy. Remember that the elastic potential energy is the energy stored in a stretched spring or the energy stored in an object under tension. You can be expected to calculate the amount of elastic potential energy an object has, and that can be done using the equation that you will find on the formula sheet. Remember, this equation is given to you on the formula sheet. You will not be expected to remember it. And that is elastic potential energy, which is there, is equal to 0.5 multiplied by the spring constant multiplied by the extension squared. Remember that elastic potential energy is measured in joules, spring constant is measured in newton per meter, and extension is measured in meters. Please do remember that equation is given to you on the equation sheet, and it will also be given in symbol form, where elastic potential energy EE is equal to a half multiplied by K multiplied by E squared. If the examiners wanted to increase the difficulty of a calculation question involving this equation, what they would do is they'd expect you to work out the spring constant K first. In order to work out the spring constant, you have to remember the equation. Force is equal to spring constant multiplied by extension. Force is measured in newtons, spring constant is measured in newtons per metre, and extension is measured in metres. Once you've found the spring constant using this equation, you'd do spring constant would be equal to force divided by extension. You would then be able to substitute the value for spring constant into here and then calculate the elastic potential energy. Or you could even be expected to rearrange it to find the extension. The spring constant equation is usually taught to you for paper 2. However, with the increasing difficulty of these exams, you may be expected to know this on paper 1. Energy can also be calculated for temperature changes. And when we look at temperature changes and energy calculations, we need to talk about specific heat capacity. So if the temperature of the system is increased, the increase in temperature depends on the mass of the substance heated and the type of material and the energy input to the system. The specific heat capacity also comes up in topic 3 particles, and you should know the definition for the specific heat capacity of a substance is the amount of energy required to change the temperature of 1 kilogram of a substance by 1 degrees Celsius. This equation is given to you on the formula sheet, and it is that change in thermal energy is equal to mass times specific heat capacity times by temperature change. The equation has the symbol E equals m times c times delta theta as shown here. Remember that E is the change in thermal energy measured in joules, all energy is measured in joules. M is mass measured in kilograms. Specific heat capacity is measured in joules per kilogram per degree Celsius. And delta theta is the temperature change measured in degrees Celsius. Please remember that delta theta, or the temperature change, can be found by doing the final temperature take away the initial temperature. So the first required practical that we need to do in physics is the specific heat capacity required practical. And the exam board asks you to carry out an investigation to determine the specific heat capacity of one or more materials. The investigation will involve linking the decrease of one energy store, or work done, to the increase in temperature and subsequent increase in thermal energy stored in the system. Now, as I approach this question, what I'd be thinking about doing, or this practical, is I think about the equation. And in physics, remember, the equation is just a mathematical representation of a law. So the equation states that change in thermal energy is equal to mass times specific heat capacity times temperature change. We are trying to calculate specific heat capacity, which means we need a means or a method of measuring temperature change, mass, and change in thermal energy. So we can start with temperature change, and what we'll do is at the beginning we'll measure the start temperature using a thermometer. We'll then heat our object using some method, and then we will work out the final temperature using a thermometer. When we heat our object, we'll heat it for a given time, and we'll time that time using a stopwatch. And you should remember that to work out the temperature change, you do the final temperature, take away the initial temperature. To measure the mass of the object, we're going to use a top-pan balance. A top-pan balance is something that you'll use in science all the time. You basically put your object on top of the top-pan balance, and it will give you its mass in grams. So to measure the change in thermal energy, we need to measure the energy provided by the heat source. And that can be done using 2 different methods. The first one, we can use a joule meter, which will tell us the energy straight away. Or, in most cases, not a lot of schools have a joule meter, so you'll need to use an alternative method, which I'm just going to talk you through now. So the steps I've gone through so far would allow you to be able to do this question, or to explain how to do this practical for any different method that you could think of using. You always go through the same process of trying to find out what you need to know from the equation, such as specific capacity, and then how you're going to measure the other things. So at my school, what we tend to use, we use a power supply, which is connected to a heater, electrical heater, and we heat up a block using that heater. We would measure the mass of the block using the top pan balance, as already said, and we'd measure the change in temperature using the thermometer. By measuring the change in thermal energy, what we would do is we would also connect a voltmeter in parallel across our heater and an ammeter in series with our heater. And once we've got a voltmeter and ammeter, we're measuring the current and potential difference. And we know that the current multiplied by the potential difference gives us the power of that electrical heater. We then need to know that energy is equal to power times time, and as we said, that the power is equal to current times potential difference, and therefore we can calculate our energy by doing current times potential difference multiplied by time. And that will allow us to calculate our change in thermal energy. Once we've got change in thermal energy, we know that. We know the mass and we know the temperature change, so we can then calculate the specific heat capacity. We're now going to move on to look at transferring electrical energy. When we discuss transferring electrical energy, we're really talking about power. So power is defined as the rate at which energy is transferred or the rate at which work is done. As I've mentioned earlier, when we talk about work done or energy transfer, they essentially mean the same thing. So the equation that you need to know is that power is energy transferred over time, as shown here. In symbol form, that is P is equal to E over T. The work done equation, we get power is equal to work done over time, so P equals W over T. Power is measured in watts, energy transferred, E is measured in joules, and time is measured in seconds. And because work done is essentially the same as the measurement of energy, then work done is also measured in joules. And you should be aware that a transfer of 1 joule per second is equal to a power of 1 watt. You should also remember that the higher the power, the faster that appliance is at converting energy. We're now going to look at energy transfers and efficiency. It is sometimes useful to compare appliances, and one way to do that is based on their efficiency. The energy efficiency for any energy transfer can be calculated using the equation efficiency equals useful output energy transfer over total input energy transfer. You can also change the energy transfer to be power output or power input. So you get the second equation where efficiency is equal to useful power output over total power input. You're not given either of these equations in the exam, you need to learn them both. However, if you just remember that efficiency is the useful divided by the total, you'll be able to remember what the equation should be in the exam. When you calculate this, you'll get a decimal between 0 and 1, and you can't have an efficiency greater than 1 or less than 0. When we're looking at efficiency, it is sometimes useful to represent our data as a Sonkey diagram. A Sonkey diagram uses arrows to represent all the output energies. There are 3 different methods you can use when using Sonkey diagrams in the exam, or there's 3 different ways the examiners might want to ask you a question. The first of these, method 1, is to use the data written on the diagram, as shown over here. So on this diagram it tells us that we have an input of 100 joules in terms of electrical energy. We can see that 10 joules is converted into light energy and 90 joules is wasted as heat energy. So if we wanted to work out the efficiency, we would just take the 10 joules, because that's the useful output, and divide that by 100 to get an answer of 0.1 in terms of our efficiency. The second method involves working out the amount of joules represented by 1 square in terms of the diagram. So here you can see that we have total energy in, which is 20 squares, and we have 10 joules of energy going in. So we can work out that 1 square will be 10 divided by 20 to get 0.5 joules per square. We can then see that our useful output energy is worth 5 squares, and we know that each square is worth 0.5. So by doing 5 multiplied by 0.5, we can find that the useful energy output is 2.5 joules. If we wanted to work out the efficiency then, we would just need to do 2.5 divided by the original 10 to get an efficiency of 0.25. If we look at the wasted energy now, we just want to double check that we've got our calculations correct. So if we look, we've got 15 squares here, and we know that each square is 0.5, so we work that out first. So we do 15 times 0.5 to get an answer of 7.5 joules, and you'll notice that the 7.5 joules of wasted energy adds to 2.5 joules of useful energy to give us 10 joules, which was input in the first place. Now we can see that we haven't created or destroyed any energy, all the energy has been conserved, and that means we haven't violated any laws in physics. The final method is just to use a number of squares in our calculation, so rather than having to work out what each square was, we could just solve this answer by doing 5 divided by 20, and that would give us an efficiency of 0.25 as well. So you can choose a method you want to use to answer the question based on the data that's provided to you in the question on the exam paper. Now let's look at generating electricity. Energy resources can be classified into 2 separate groups. They're renewable and non-renewable energy sources. Renewable energy resources can be replaced or regenerated and will never run out, at least not for a very long time. And examples of these resources include solar and wind. Non-renewable energy resources will eventually run out, and once they've been used, they cannot be used again. Examples of non-renewable energy resources include coal and oil. We're now going to look at the different methods you can use to generate electricity. For all the different methods used to generate electricity, you need to be able to talk about the advantages and disadvantages. You should also be able to talk about the impact they have on the environment and their reliability to meet our energy demands. The methods of generating electricity that you need to be aware of are solar, fossil fuels, nuclear, biomass, geothermal, wind, wave, hydroelectric, and tidal. Solar cells can be used to generate electricity directly, and there is no need to use a turbine in the generation of electricity when using solar. The main advantage of solar cells is they can be used in remote locations. You don't need to rely upon the national grid to transfer the energy or electricity from the solar cell to the place where the electricity needs to be used. The disadvantage of solar cells is that they're not always reliable, and you need to have sunny conditions in order for them to produce their maximum amount of energy. Solar cells aren't the best method of generating electricity if the climate's not really suited for it, so it's often cloudy, and also they don't produce any electricity at night time. Fossil fuels, nuclear, and biomass are all examples of thermal power stations. This means that the fuel is used to heat water, and the heated water turns to steam, and the steam drives a turbine that turns into a generator that produces electricity. Fossil fuels are coal, oil, and natural gas. Fossil fuels are really good at producing electricity because they're very reliable and they can produce energy or electrical energy all the time. The main drawback to fossil fuels is they produce greenhouse gases. Greenhouse gases produced by fossil fuels can be reduced if you use the carbon capture technique. Nuclear power stations use nuclear fission to generate energy that's used to heat up water. Nuclear power stations are a reliable source of energy. They can produce electricity all the time. The main problem with nuclear power stations is that they produce nuclear waste, and that's not very well liked by the public in some cases, and also they can go into nuclear meltdown. You should also remember that nuclear power stations or nuclear fuel produces the most energy per kilogram compared to all other fuel sources. Biomass is an example of a carbon-neutral fuel source, and that means that the carbon dioxide taken in to grow the plant is equal to the carbon dioxide that's released when the plant is burnt to generate the heat to make the electricity. The main advantage of biomass then is that no net carbon dioxide is added to the atmosphere when the plants are burnt. However, the problem with biomass is that you need a large amount of land to produce the crops that would then go on to be able to produce electricity. Geothermal power stations can work in one of two ways. First of all, you can use the hot rocks to heat up water that then turns to steam, and the steam would drive a turbine to produce electricity. Or you can get steam directly out of the ground that turns the turbine directly, and it doesn't need to heat up water first. The advantage to geothermal power stations is that there's no fuel costs because the energy is coming directly from the ground. The disadvantage of geothermal power stations, and the reason they're not used as widespread as some of the others, is that they're only available in volcanic regions. So we can't get geothermal power stations in the UK. Wind turbines are a good source of electricity generation. The main benefit of wind turbines is there's no pollution, so they don't produce any carbon dioxide or anything like that. The difficulty with wind turbines is that they depend on the wind, so they're not reliable. In wave turbines, what you use there is you use the power of the waves to turn a turbine. Waves are good because there's no fuel costs, it's a free energy source, and there's also no pollution. However, it does damage habitats, which is a disadvantage. Hydroelectric power stations are probably the most reliable of all the renewable sources, especially pumped storage power stations. Remember that in pumped storage power stations, water is pumped back up to the top reservoir during periods of low demand, such as at night time, when electricity is being produced by other renewable energy sources such as wind, and that means that you've always got a constant supply of water in the top reservoir. Remember that hydroelectric power stations produce their electricity by dropping water from a high reservoir to a low reservoir. As the water falls, it goes past a turbine which it turns to produce the electricity. The other problem with hydroelectric power stations is that they damage habitats. So sometimes you have to flood areas in order to build the dams, and it can damage habitats for wildlife. The source we're going to look at is tidal. Tidal barrages work by having an area of the sea blocked off, so the sea will come in, the water will go past the gate, which you can then lower if you want to, and then you can hold the water behind these gates, and when you raise the gates up, the water will flow out, and that will flow past your turbines, which it will turn. The turbines will then turn a generator, and that will produce electricity. Tidal barrages are brilliant because they're reliable, so you always get a set amount of energy from them, and you can also control that by the use of the gates. And there's no fuel costs involved in tidal barrages. The drawbacks to tidal barrages is it can damage habitats. because it will block off part of the sea, and also it's not good if the local economy depends on the sea, for example, such as it's a tourist attraction in that area, because you're going to put a big tidal barrage in the way, and also if you need to get in and out of like a harbour or an estuary. So there I've just run through a few of the different advantages and a few of the disadvantages for each method of generating electricity. You should be aware that you need to know 2 to 3 advantages and 2 to 3 disadvantages for all the different methods of generating electricity. So this is just a warning that the content that comes after this slide is for the triple only candidates. If you're doing combined science, I suggest you turn the video off now, whereas if you're doing the triple course, please continue to listen. So the only piece of content that you need to know for the energy topic, if you're doing the triple course, is the thermal insulators required practical. And the information given to you about this practical from AQA is that you need to investigate the effectiveness of different materials as thermal insulators and the factors that may affect the thermal insulation properties of a material. That is essentially 2 different practicals, and we're going to look at both of them now. The first practical is investigating the effectiveness of different materials as thermal insulators. To do this, you're going to measure the rate of cooling of a beaker of hot water when insulated with different materials. You're going to use a stopwatch to measure the time and a thermometer to measure the temperature change. I imagine what you're going to do is you're going to record the time on your stopwatch, and at every interval, such as 30 seconds or a minute, you're going to mark down the temperature at that point. That would then allow you to plot a curve or a cooling curve, and the beaker or insulation of a beaker that cools down the least is going to be your best insulator. The second practical is investigating factors that affect the thermal insulation properties of a material. In this case, what you're going to look at is a way of changing a material to try and see if it will be a better insulator or not. So here you're going to measure the rate of cooling for a beaker of hot water when insulated with different thicknesses of the same material. So what you're changing this time is the thickness of the material. You're going to measure the time taken with a stopwatch again, and measure the temperature change with a thermometer. And again, as I mentioned, you probably record the time, and every 30 seconds or so you would record the temperature, and then you plot a graph of time along the x-axis, temperature change on the y-axis, and in that case you draw a curve. The thickness that gives you the greatest amount of insulation will be the curve that has the lowest temperature change. That brings us to the end of the energy topic. I hope you found this video useful, and I wish you luck in your exam.